All right, thank you for joining us today. For today's CyLab seminar, we welcome back Adrian Perrig. And Adrian is a professor of computer science at the Swiss Federal Institute of Technology, or ETH, in Zurich, where he leads the network security group. He is also a distinguished fellow here at CyLab and an adjunct professor at Carnegie Mellon University. From 2002 through 2012, he was a professor at CMU. And from 2007 to 2012, he was CyLab's technical director. Adrian's research revolves around building secure systems, in particular future internet architectures. The subject of his talk today is exciting security research opportunity, the next generation internet. So please join me in welcoming Adrian back to CyLab.
Great, thank you. Yeah, thank you very much. It's always a joy to be back. So I'm going to be talking about our future internet architecture and, in general, problems and issues with the current internet and how we could possibly fix them. So if you look at today's internet, one picture you could have is it's kind of like the pyramids. It's a monumental structure that has stood the test of time and cannot be easily changed or cannot be changed. But the more you know about the internet, and I hope to convince you that it more resembles a structure like this. It's ancient, unstable, and a bit brittle. So I'm going to look at 4 issues in today's internet that we're struggling with today, and they are control, transparency, availability, and trust. I'm first going to talk about trust. And in the early days of the internet, people trusted each other. There were not that many users, and they all knew each other. And there's a nice TED talk by Danny Hillis you can look up. And one of the quotes of this talk was that there were only 2 other Dannys. Essentially, he had a book with all the people who had email addresses on the internet at the time. And literally everybody knew everyone else. And it was a trustworthy environment. Now, this has changed a little bit, right? You could still probably make a book with all the email addresses, but that would be a little bit big to carry around with you if you printed it. And the issue is that we today have so many entities, people on the internet, that you cannot trust all of them anymore. And this heterogeneity of the global environment really complicates authentication infrastructures. And this is relevant in the context of authenticated routing updates, DNS replies, or authenticating TLS certificates. And currently, we use 2 different models for authentication of internet entities. One is called the monopoly model. The other is the oligarchy model. I'll first talk about the monopoly model. And here, you have the whole world agreeing on a single root of trust that is being used to authenticate different entities. So an example is RPKI, the resource public key infrastructure that's used to authenticate BGP-SEC messages, or DNS-SEC replies that are essentially authenticated based on a root of trust you use to verify digital signatures. And so the problems with this, of course, are many. The first problem is the whole world has to agree on a common root of trust. Right? There's one single key, essentially, that rules, and whoever has that key can rule over all the authentications. And that single key, of course, not only agreeing on it is an issue, but also it's a single point of failure. If someone discovers this single key, they can do a lot of damage. Also, the revocation can be inefficient, and the update mechanisms can be inefficient of changing these keys or changing the master key. And that can cause also many problems if we'd have to update this key. On the other hand, we have the oligarchy model, which is not much better in terms of issues. In the oligarchy model, we have a very large or several roots of trust that we need to rely on. And the TLS PKI is an example of this root of trust, of this oligarchy model. And today, browsers trust on the order of 1,000 different root certificates that can be used to verify any of the TLS certificates our browsers receive. Now, the issues with this, of course, is that there's a single point of, or many single points of failures. Any single compromised root of trust can create an arbitrary TLS certificate. And so also the revocation and update of these roots of trust are done via operating system updates or browser software updates, which can take on the order of days or at best, or even weeks, until a large fraction of users has updated their browsers or operating systems. So this is also a big issue in today's internet. The question is, how can we address this? And a proposed approach that I would suggest is having different isolation domains. So the observation is, if we split up the internet into different parts where within each part people can agree on a root of trust, then we can have one different root of trust for each of these isolation domains. And so we can then authenticate users, or say routing updates or DNS entries within each isolation domain. And this actually will also help for the modern ways for forming public infrastructures. Maybe people have heard of log-based public infrastructures like certificate transparency by Google, or systems we've built in our group called AKI or ARPKey, which is going to be presented at CCS this week. And the problem these new systems have, these log-based systems, is that they essentially require logging of the certificate in a public log. But the question is, which public logs are trusted? So we're getting back to the same place, that in the whole world there will be a very large, possibly a large number of logs. And now all these logs are again trusted, and we're kind of back to square one. And these systems could also benefit from isolation domains where it would be clear which log would need to be consulted given which certificates. Now, a challenge when you split things up in this way become that global verifiability becomes an issue. So different users would also likely have different roots of trust, and they would start their validation or authentication mechanisms based on their own root of trust. And you want to make sure that any user can still verify any other entity in the world, and that's one of the challenges in this space. So let me come to the second issue, the one of control. And we have essentially several issues in control. The first one is who controls the internet itself. And we have different governments who would like to have more control over the internet. So in Europe, there has been a call for what's called a Schengen network, which would exclude the United Kingdom. And also Brazil, Russia, China, different countries have asked for more autonomy. And so isolation domains, as I mentioned in the previous slide, could also help to simplify the governance structure for the internet. Another issue is who actually controls internet paths themselves. So it turns out the current internet offers very limited control of paths. Even ISPs who propagate what's called BGP update messages, they have limited control once the BGP update message leaves, once they send it off. Because other ISPs can then decide which updates they propagate, and consequently, even a destination or ISPs on the path have very limited control over how traffic reaches that destination. Also, we've seen that internet paths can be hijacked or redirected, and Renesys nicely documented this. And here I'm showing 4 examples of such redirections, which turn out to be a lot more frequent than people assume. And in this first example that Renesys documented is a communication from Guadalajara, Mexico to Washington, D.C. And these packets go across London, Moscow, and Minsk. In this other example, traffic from Denver to Denver, in the common case, funny enough, would go via Dallas and Kansas City. But what they've measured is that this traffic went through London and Iceland. In this example here, traffic from New York to LA, again, went through London, Moscow, and Minsk. And in this example, traffic from Chicago to Tehran is crossing the Atlantic Ocean 3 times. So there actually have been a lot of these examples where traffic flows in unanticipated ways across the internet. And so an interesting question is, who actually should control the routing paths? So it's clear that ISPs need to have some amount of control so traffic respects their forwarding policies. But the question is, how much control should endpoints get? So we have a range from no endpoint control at all, which is pretty much what we have today, to complete endpoint control, where we essentially have source routing, where an endpoint decides on the entire path. But I would argue that both of these extreme cases are suboptimal. No endpoint control is not desirable because endpoints do or should have some level of control, but complete endpoint control is also problematic because endpoints could launch attacks, for example, by creating a lot of traffic that goes through a certain part of the internet and causing congestion in those areas. And so endpoints should not have complete control over their routing paths. And so the suggestion is to provide limited endpoint control. Now the question is, what do you mean by limited? And I'll be getting into this in a minute. The third problem I'm going to address is transparency. And here also we have different cases. So in transparency of internet paths, we would like to have that an entity who sends a packet knows what's going to happen to this packet. The sender essentially would know where this packet or how this packet traverses the internet. Now it turns out that this is absolutely impossible to achieve in today's internet. You could state that, well, a source could download all the BGP updates from the BGP protocol to kind of predict where this packet is going to go. But unless you actually know the state of the routing tables in each router, you cannot know where your packet really is going to go. And in order to get very strong assurance, you essentially, so essentially today a sender cannot get strong assurance of where the packets are going to go because of these aspects. And so a proposed approach would be a packet carried state, where the packet contains the forwarding information. Now this issue is actually orthogonal to the issue of control. Essentially, even though the source node puts in essentially the forwarding path into the packet header, does not mean that the source has full control, because you can have mechanisms that limit what types of paths can be put in the packet headers. So that's actually an orthogonal issue to the one I mentioned earlier of path control. Another point in transparency has to do with the transparency of trust roots, and to know for a user which entities need to be trusted for a given authentication event. So for example, today users have very little information when they visit a web page. And while users should not have too much information, they should have some amount of transparency whom they have to trust, and also have some level of control as well about which entities they really want to trust. And so isolation domains also help in this space to limit the amount of entities users have to trust, and possibly also to provide more transparency for each entity that they want to authenticate. The last problem I'm going to look at is the one of availability. And today we actually have relatively poor availability in today's internet. If you have a well-connected entity, you only get about 3/9 of availability, which corresponds to about 1.5 minutes outage per day to some of the parts of the internet. And Katz-Bassett et al. Published a nice paper measuring availability in today's internet at SIGCOMM 2 years ago. And they essentially found and documented these numbers that you, with quite a bit of effort, you reach about 3/9 of availability, and an Amazon data center would reach, with a lot of effort, about 4/9 of availability. Now, the reason availability is low is because there are numerous short-lived outages when BGP the Border Gateway Protocol performs a route change. And there are also route convergence delays that hamper availability. Then there are outages due to misconfigurations and also outages due to attacks. So prefix hijacking can be used to redirect the route, but also to make a certain destination unavailable. And so some people may sit there and think, well, 3 nines of unavailability or even 4 nines may be enough, right? Why do we need more than that? But I believe that even 4 nines of availability still represent about 10 seconds of outage per day, and that is still insufficient for some important application. So for example, if we use the internet for critical infrastructure command and control, for our traffic control or smart grid control, we would like to have a network that provides a higher level of availability than just 4 nines. Or if you have an internet-based business, or if you perform financial trading or transactions across the internet, or also in telemedicine, maybe another area, then you would like to have higher levels of availability without spending millions of dollars to actually purchase a lot of different connections to different ISPs. And so the proposed approach to achieve better availability would be to actually replace BGP. And the BGP today actually faces a lot of different issues that also go back to the issues I mentioned here. So in terms of trust, it has a single root of trust. As I mentioned earlier, it allows very limited path control. It has provides no transparency or no guarantees where your packets will actually be sent. And availability is hampered by the fact that there are frequent outages when paths change. And there's also slow convergence in BGP during this iterative route computation. And it's also susceptible to attacks and misconfigurations. Although BGP-SEC fixes some of these issues, it introduces new problems. But unfortunately, I don't have time to go into these issues. So to fix BGP, you may say, well, let's make small changes. But my claim is that scaffolding and making small changes is not enough. We really need a new foundation for our network. And so if you think about evolutionary versus revolutionary, I believe that some of the problems cannot be solved by making small changes. You really need a completely new protocol to solve some of these fundamental issues. Also, a revolutionary approach is desirable because when you start anew, you can take care of a lot of the issues all at once, and you can create a new clean architecture that addresses these issues. And also I hope to convince you that actually a revolutionary approach is possible through an evolutionary deployment. And in fact, that you can use IP, for example, for local intra-domain communication and only change a small fraction of border routers to replace BGP. Also, you can simultaneously operate when you have a new protocol with the current BGP protocol. And the hope also is when your architecture has really strong properties, that there's actually incentives to deploy this new architecture. And this was something that when people think back at a lot of the revolutionary approaches, they have not offered sufficient strong properties that warranted a switch to the new architecture. So there have been a lot of proposed internet architectures that people have studied. And I can't really go through all of these. One of the major ones are the Nimrod architecture. And currently, there are several groups of researchers looking at future internet architectures funded by the NSF, and that includes XIA, Mobility First, Nebula, and we had also NDN and ChoiceNet are other examples of this. And also NewArch has been another of these architectures. Now, with respect to the first category, most of these architectures also target a basic BGP replacement or basic new routing architecture. But a lot of the future internet architectures are also looking at how to more efficiently deliver content. And examples here include NDN, CCNX, PSERP, or an architecture called SAIL and NetInf. There have been proposals to enhance routing security. There are also proposals for path control and many, many other proposals. So almost any three-letter acronym, there has been some project with that acronym. But the focus that I believe is becoming more pressing is really a security focus. So none of these projects really had security and availability and to fix all these issues as a major focus. So with this in mind, we started the Scion project, which stands for Scalability, Control, and Isolation of Next Generation Networks. And there are currently a number of people in my team and also with collaborators helping to work on this project. So the architectural goals of Scion are as follows. The first is high availability. So we'd like to have and being able to use a path as long as an attacker-free path exists. And this is one of the big issues in today's internet, where one compromised entity can prevent communication for surrounding entities. And ideally, as long as the adversary cannot have management plane level access to a sequence of routers, it should be possible to use this sequence of routers for communication. And we'd like to achieve this property. The next property is a secure entity authentication that scales to a global environment. Next is flexible trust. So we can operate in a heterogeneous trust environment and also enable end users or domains to make decisions about which entities they want to trust for their entity authentication. We'd like to have operation transparency, so it's clear to the sender and receiver what happened to their packets and who needs to be relied upon for delivering packets or for general network operations. We'd also like to have balanced control among ISP senders and receivers, and of course also have scalability, efficiency, flexibility, so that it's economically viable to deploy and use this network. So the first part of Scion I'm going to present are the isolation domains. And these are mainly due to the fact that we want to deal and cope with heterogeneous trust in today's internet. And so the definition of a trust domain is to have a region which entities in the region can agree who should control the root of trust within that region. And so also the region should agree upon a set of ISPs that manages this isolation domain, and we call these set of ISPs ISD or isolation domain core. Essentially, they manage the trust routes, but also are important for the routing and connectivity to other isolation domains. Then, if you look at this, it is actually still an open research issue exactly how to structure these ISPs, because there are a lot of political and legal issues that come up when you start drawing out these isolation domains. A possible partition with which I'm going to work with during the talk is to use geographical regions as isolation domains. So the assumption is that a set of geographical or a set of countries could possibly agree on a root of trust and also manage and maintain this root of trust. So in Scion, the isolation domains, I'm going to draw them as one of these blobs. And you can see the ISD core. And here on the right, you see 3 autonomous domains that manage this ISD core. Each circle represents an autonomous domain. And they connect to each other in the same way today different autonomous systems connect to their providers or they connect with peers via peering link for the actual routing. Scion uses a new approach for the communication itself, how to find paths. And the way it works is that the ISD core ADs, so these 3 black circles, initiate route construction or path construction beacons. And what this is essentially a scalable and secure way to disseminate topological information. It works as a k-wise multipath flood to provide each autonomous domain with multiple entities. So after this flood, essentially each end domain will know several different paths, how they can reach the ISD core. And here we see a number of different paths that were learned by different ADs. So it's a single multipath flood. Now the way this is used is we have a path server that's operated by the ISD core, and destination domains can select paths under which they want to be reached. For example, the red autonomous domain, blue and green AD, they select under which paths they want to be reached, and they upload these set of paths to this path server in the ISD core. Now, if the blue host within the blue autonomous domain wants to communicate with the host in the green autonomous domain, it would fetch the paths to reach the green autonomous domain, and it would combine one of its own blue paths with one of the green paths that it has learned. So note that any of the blue paths would work with any of the green paths, but in some cases, for example, if you combine this rightmost blue path with the leftmost green path, you then have a shortcut that prevents the packet from going through the ISD core. So the packet could then directly travel along this black path, which is a short path in this example here. So you notice here that a lot of the properties I talked about are already achieved. It's this very simple beaconing process with this selection of paths and then this combination of one up path and one down path. And the first advantage is this point of balanced route control that I mentioned earlier. Essentially, the ISPs have a control over which beacons they forward. So they have control over which paths are being announced. The destination has control over how they can be reached, right? They control which paths they want to upload to the path server for other nodes to reach them. Then the source also has control because the source can select its own path and select one of the destination's paths to be combined to form the end-to-end path. And so you see all parties are involved to have some level of control, but no party has full control. So the sender could not simply select arbitrary paths to use. So the sender doesn't have full control. It can only combine one of its paths with the destination's paths. Also a nice property is that Scion isolates forwarding from the routing itself. So once the packet contains this black path, the control plane or the routing protocol cannot influence this packet from reaching the destination in this way. So even if there could be some attack on the routing protocol or anything, this or any strange event in the control plane of the network, the actual data path, this black path, cannot be influenced anymore. And that offers a lot of resilience to attacks. Also, the transparent forwarding is an important property. The source node knows exactly which path the packet is going to take. And that offers this transparency property. And the nice efficiency property is that routers don't need forwarding tables anymore for the border routers. Essentially, the packet contains the path at the level of the autonomous domains with ingress and egress interfaces. So a router at the ingress interface of an autonomous domain would already learn the exit node at its autonomous domain and would not need to look up any routing tables. Now let me give you a little bit more detail about the path construction itself and the cryptography used to protect this. So we have this path construction beacon traversing from the blue AD to the red AD. And what's in this path construction beacon is a expiration time, as well as the interface shown as the blue triangle, that essentially the location where this path construction beacon exited the ISD core. Also, what's contained is an opaque field and a digital signature. the opaque field is going to be used for the forwarding itself. So that's a 8-byte blob that an ISP can fill in any way it wishes to forward the packet in this way. So at the minimum, the interface itself is part of the opaque field, along with a message authentication code computed over the expiration time and the interface itself. And the key for this message authentication code would simply be a local secret key. So that key does not have to be shared. It could even be a unique key per router that does not need to be shared with any other router or any other entity. Also, to make it verifiable to destinations, to explain to destinations or other entities that this is the correct information, we add a digital signature that's shown here over this entire path construction beacon so far. The next autonomous domain then adds this additional information for the information it sends on to the green autonomous domain, which is its own ingress and egress interfaces shown with the two orange triangles. And again, a message authentication code that's computed with a local secret key, and now also computed over the opaque field of the previous ISD, or of the previous autonomous domain. Because we want to prevent cut and paste attack where different opaque fields would be arbitrarily combined. By using this linking, we can prevent this kind of arbitrary combination. As well, a digital signature is computed over the whole path construction beacon up to that point, which includes a signature over S1 itself as well. Now, when the green autonomous domain receives this information, it can verify all the digital signatures, and it can already make use of the two opaque fields, O1 and O2, to communicate with this ISD core. So simply having a single of these beacons allows the destination, for example, to upload a set of paths to the path server in the AD core, ISD core. Now, intra-ISD communication, of course, is possible. And here I show an example where we have a node I in ISD3 and nodes C and F in ISD1. And here, if node C wants to communicate with node I, it can also contact ISD3 and download the local path and combine it with a set of, combine its own up path, its own path to its ISD core, to a path amongst the ISD cores, and then the path finally from ISD3 to the node I, to the actual destination. So the paths are being combined, including a selection of how the packet traverses the different ISD core network, which you can see at the top. So essentially, this is what I just said. Now, Scion would not be that efficient the way I've presented it so far if it were not for a rule how peering links can be used. So a peering link would be a link, for example, between AD B and E, which both autonomous domains agree to exchange traffic with each other. But there's some restrictions on how these peering links can be used. And essentially, how we use peering links in Scion is when this red path is being announced in the path construction beacon, the autonomous domain B adds the peering link to the beacon message itself. And if E also announces the same peering link to its beacon, then communication from C to F can directly go across this peering link. But cryptographically, it's required that both entities announce the same peering link. And then even though the red path and the blue path don't intersect except at the ISD core, the communication can go across this peering link from C to B to E to F. This even works across isolation domains. So if there's a peering link between E and H, that can also be announced in the beacon, and it can be utilized for communication, say, from F to I. And this is very important to form short paths in many cases. So what's important in Scion is that the sender always has full information what is going to happen to its packets. So if one of these intra-ISD links, peering links is being used, node F knows precisely when the packet is going to leave its isolation domain and which other isolation domain the packet is going to go to. So it's the transparency is still maintained even in this case here. Now, some of you may wonder, well, what about link failures, right? If the packet contains the forwarding path, what happens if a link fails? Well, if a link inside an autonomous domain fails, we assume there's a separate routing protocol inside this autonomous domain that the packet will still make it to destination. Essentially, Scion only dictates the ingress and egress interfaces within an autonomous domain. Inside, how the packet traverses that network doesn't really matter. But of course, also border router may fail, etc. And so what we do in Scion is, by default, we use multipath forwarding. So for every socket that we create, we attempt to use several paths at the same time. So if there's any single path that fails, hopefully there is one of the other paths that still works correctly. A second technique that we make use of is that path construction beacons are constantly sent. So even if links fail, hopefully the sender will continue to receive a number of beacons that are functioning. Moreover, when a link breaks, we immediately send a message to the ISD core to erase all paths that contain that link, so that at least entities who fetch links do not learn paths that are not usable anymore. And we also immediately create an additional flood of beacon messages downstream to create quickly new paths that are in use, that are functioning. So the current implementation status of Scion is that everything and a lot more than I talked about is fully implemented. We almost completed the first full specification of the first basic protocol with all bells and whistles. And we have, we're working at the 4th generation of the code itself. So generation 1 and 2 was based on the click modular router. And then in generation 3, we had a native C, C++ implementation, achieving much higher speeds. And we're currently rewriting this in Python to enable new people who want to use Scion to quickly understand the code and also contribute and use code. We also have a high-speed router implementation where on a single off-the-shelf PC, we can switch 120 gigabits per second on that host. And I added up all the time we've already spent on this project, including collaborators and summer interns. And I came up to about 50-person years of effort we've already spent on making this work. And so it is actually fully functioning protocol. And there's a node here at CMU you can use to send Scion packets. So in fact, all over the world, we have Scion nodes that form a topology similar to the one you can see here. And it's working. We've done video conferencing over Scion between ETH and Korea University, for example, or between ETH and CMU. And it was actually using Scion headers. So the Scion header, packet header itself, although I don't have time to go into details, looks as follows. There are only 8 bytes of common header. Everything else is optional or potentially variable. And so even the source or destination address are optional because Scion doesn't really have routing tables or forwarding tables. And so there isn't really a need to have a source or destination address for the delivery to the destination autonomous domain. So, but there's a lot of flexibility built into the protocol, including extension headers that are used for a variety of extensions that we've built, such as fault localization extensions or network capabilities, as I'm going to talk about in a minute. So next I'm going to talk about a number of applications and how Scion could be used. And the first one is application in the trust domain. Then I'll talk about transparency, how to provide source authentication and path validation. And finally, I'll briefly talk about network capabilities for DDoS defense to provide more availability. And the trust root management in Scion is essentially per ISD, per isolation domain, we have these trust roots. And what's cool about this approach is that we have a trust root configuration file that serves as the root of trust that makes it very easy to update and create, change the trust roots and quickly disseminate this information to all entities within the isolation domain. So I best show this based on an example, which I show here. So assume we have the EU ISD core, and this Switzerland would be the small isolation domain on the right. And the EU ISD would have one of these root of trust files, which contains a version number, a set of certificates that are the main trusted roots of trust inside this isolation domain. And what's important is an update policy. So here we say, as long as 2 out of the 3, or I should say at least 2 entities sign a new TRC file, that new TRC file is becoming active. And so then there are digital signatures with these keys of the keys that are valid in version n-1. Each ISD would have its own root of trust file, and there is cross-signing of different root of trust files. So for example, here we see the Swiss at the bottom. The Swiss ISD trust root configuration file would be digitally signed, for example, by key KA, the private key KA. And therefore, you can, if you have a root of trust file that you trust, you can then verify root of trust files in other ISDs very easily. Also, we're using this to verify autonomous domains within an ISD. So here we see a certificate for node D that's also signed by A's private key. Now, what's interesting is how this can be easily updated. So let's assume one of the entities, let's say B, has updated its key. So any other 2 entities can now get together to update B's certificate in the TRC file and create a new version. So they essentially just sign it and post the new version. Now for every path construction beacon that gets sent out, it also carries this TRC version number, because this beacon states how it can be verified. And in this example here, once the beacon goes out, all the entities receiving it can then notice that they have an old version of this TRC file, and they can go wherever they received the beacon from and ask to have an updated TRC file. And so with a single dissemination of a route construction beacon, the whole network quickly learns this new TRC file. And what's nice about it is you don't need an OS update or a browser update if one of the roots of trust needs to be updated. And within minutes, the whole network will have the new information. So these per ISD trust root configuration files enable heterogeneous trust roots and enables very fast and efficient update and revocation. And so an observation that we had is actually every network architecture should provide a mechanism for efficiently disseminating roots of trust and efficiently updating roots of trust. Because say if you use roots of trust for DNSSEC or for TLS PKIs or for routing messages itself, it is part of the network operation to provide authentic ways to authenticate these entities. And therefore, the network architecture should provide ways to also maintain these roots of trust. Next, I'll briefly talk about source authentication and path validation that was enabled by the way Scion operates. And so in path validation, a receiver wants to verify that the packet followed exactly an intended AD level path. And in source authentication, in this case, source authentication enables routers to verify the sender as well as the packet contents. We published this work this year at SICOM, and I'll provide a brief overview of how this works. And hopefully I can demonstrate how Scion can be used to provide such a mechanism efficiently. So here you can see that to provide the basic source authentication, each router could share a secret key with the source, and then the source simply adds a message authentication code per router. So this would be an easy way to provide source authentication, so each router can verify this information using an efficient message authentication code on each packet. And so it's clear that if each router shares a key with the source node, then the correct MAC could only have been generated by S if the router didn't generate it itself. So path validation can also be very, very simple by using a related approach. Essentially, the source node can share a key with each router, so each router can know it's really that source node who sent it, but also then each router can in turn share a different secret key with each other router on the path, so the routers could all cross-sign information. So for example, the source can use this blue key, so R1 can verify the source, and R1 can share the yellow key with router R2, and then R1 can create a proof to R2 that it has seen the packet. Now, R1 would also have to do this for D and so on. So you could do this in turn for every subsequent node on the path, which can be quite expensive though, unfortunately, but this is a simple example to show the basic concept. Now, one issue that all the previous source authentication path validation schemes suffered from is what's called the coward attacks. And essentially, all these schemes needed to set up all these keys before a packet was sent. And all the routers would set up these keys with all the other routers on the path and with the source. And so, of course, if a router wanted to misbehave, mistreat and missend some of the traffic, that then the router would know that now it could be detected if it cheats, and it could start behaving correctly. And so this is what's called a coward attack. Now, what we've done is we created a mechanism that enables key setup after the fact. So essentially, instead of requiring key setup and then performing origin and path validation, our protocol is called OPT, standing for origin and path trace, origin and path trace. We created a retroactive version where first you send the packets, and subsequently all the keys are being set up, and then subsequently all the packets can be locally verified. And the way this works essentially is to have routers compute all the keys dynamically that are being used with any other router or with the destination. So essentially, each router only has a local secret, and it can use this local secret to set up the keys it needs with the destination or with any other router. And we noticed that this key setup can be extremely fast. So for example, by using some parameters, constant parameters in the packet header, plus a local secret, a router can use an efficient pseudorandom function for which you use AES to very quickly derive a key. Actually, it turns out that these keys can be derived within 40 cycles on a fast CPU today. And 40 cycles is very fast. It can even be faster than a memory lookup. If you have to go to main memory, it takes as much as 200 cycles on a modern system. And so deriving the keys can actually be much faster than looking up the keys in main memory. Now, caching, of course, also gets you down to about 40 cycles for a cache lookup out of level 3 cache. But still, it can be advantageous to dynamically derive all the keys. Then you do not have any issues with packet state or per flow state in routers. And also, this derivation enables this property of retroactive key setup. So we're able to create a system that called OPT that required constant computation during forwarding, no matter how long the path was, also and only requiring 2 message authentication codes per packet to perform these operations. Let me actually skip over the details because I don't really have time to handle all this. So let me just spend one slide on how to use network capabilities in Scion. And for people who know about network capabilities, it's essentially a cryptographic identifier for every node on the path of the packet that can be verified by that node. In Scion, these opaque fields I described are essentially like network capabilities. So already Scion, the way Scion operates, it essentially already uses a form of network capabilities that can simply be turned on and used directly to implement easily these stateless network capabilities to provide ways to filter DDoS traffic in the network and so on. And we have a paper called Stride where we go into more detail of this mechanism. And Scion essentially provides this stable path. So the reason this is not as easy to do in today's internet is because paths could change at any time. So capabilities may, if the path changes, capabilities essentially become are not the correct capabilities anymore for the new path. So every time the path change, you would have to set up a new capability. So if there's some load balancing and packets bounce back and forth, then you could be unlucky because unless your packet takes exactly the same path as for its active capabilities in the packet header. But in these systems like Scion, where the forwarding path is in the header, you have essentially an ideal case for using such network capabilities. Now let me briefly talk about incremental deployment. And it actually turns out ISPs need to perform very minor changes to deploy Scion. Essentially, they need a beacon certificate and path server, which is simply a server they set up. And they can internally use the regular MPLS, IP, or SDN forwarding, whatever they use internally. And if in the beginning, you can set up IP tunnels amongst ISPs that deploy Scion to bridge ISPs that do not deploy Scion. And we found that also in end domains, only minor changes were required because you can already make use of local IP level routing for basic connectivity, and you can set up a Scion gateway that then adds a Scion header and uses intermediate IP headers to get the packet to the next Scion node. Here's an example of how this can look like. We see one domain at the bottom right where we have 3 edge routers that are updated with Scion. And internally, you have all the traditional switches or forwarding entities. And so the packet can, if it has to get from one ingress interface to an egress interface, the local internal forwarding will be used. So for example, we would add an IP header if IP switching were used, or we can add an MPLS header if MPLS switching was used. Now we have also implemented a project that we call the box, which makes it very easy to update and provide Scion for endpoints that you cannot easily update. So for example, we have a smart meter here connected to ADF and a management station at ADI. We built this box which has essentially 2 interfaces, 2 Ethernet interfaces, and you put this box in between the network connection. So you would put one box between the management station and one box between the smart meter and its connection. And now what the box is doing, it essentially observes IP traffic. It doesn't do anything initially except just observe what's happening. And the two boxes detect each other in a way that no extra packets are being sent. Now, if the two boxes detect each other, then they start a protocol to also learn their Scion addresses, and they start setting up multiple Scion paths between each other. And now they're still watching the IP traffic as it goes on, which still traverses the regular IP network. And if they can detect that there's some packet loss or some IP level outage, they encapsulate the packet inside a Scion header and send it across the Scion network, which hopefully will not suffer from the same issues. So very simply, you can use such an approach, and it's already working today. So it becomes very simple to update your network with this mechanism. So in summary, Scion is a complete redesign of a network architecture. It solves a lot of the issues we have in today's internet, especially BGP protocol convergence issues. It separates control and data plane. It isolates mutually untrusted control planes. It offers path controls, simpler routers, these roots of trust that can be selected per isolation domain. And so if you look at this, it's essentially an isolation architecture for the control plane, but for the data plane, it's really a transparency architecture. So when source and destinations want to communicate, they essentially obtain a lot more information of where packets are going. And that's why I would call it a transparency architecture for the actual sending, because still any host can communicate with any other host. So it's not an isolation architecture for the actual communication, but only a transparency architecture for the actual end-to-end communication. But it does isolate the control planes and prevents a lot of attacks that way as well. So we have a number of published papers that describe some of the things I've presented. And in conclusion, I would like to emphasize 3 points. So I hope you agree that a deployment of a new internet architecture is necessary, and it's actually also possible. Not much has to change, not much has to be upgraded to start making use of a new internet architecture. And I hope that high-value applications of the internet will require strong properties, and that can drive deployment of such a new architecture, which can actually run simply in parallel to the current internet architecture. So hopefully also members of the research community will contribute, because there's an abundance of research challenges once you look at the new internet architecture. And so there are also legal issues and political issues, as well as public policy issues, that require interdisciplinary research to address them. So then the last point is we make one proposal for such a future internet architecture that addresses a lot of the issues we have today. And Scion simply provides secure and entirely available end-to-end communication. So it's not a architecture for data-centric communication or multicast or mobility, but it's really a simple architecture to replace BGP, for example, simple end-to-end communication. So with that, I would like to thank the team who actually is doing all the work. And here is outing that we had, not an outage, outing in the Swiss mountains. And so these are the guys who are actually doing the work. So thank you so much for your attention. I'll be happy to answer questions you may have. Okay, thank you. Right. Mm-hmm.
So with Scion, if I was understanding correctly, Scion tends to, in the signing and verification that Scion does, I got the impression, and correct me if I'm wrong, that is happening on the, basically the border, or so you called it the core. And so when you're in your diagram, it looked like at the core, that was essentially the higher tier, the high processing components of the network. And in normal network design, you really, you're familiar with the core distribution access model, which tries to avoid additional policy enforcement and additional computational things like signing and verification at the core. And so I was wondering if you could either clarify my misunderstanding or explain how a system like this can kind of scale when you may be doing signing and verification higher up in the high-load networks.
The actual signing is only done in the beacon server, so the edge routers don't even need to do that. But the signature is not carried in the actual packets, so only the message authentication code is being carried. So each autonomous domain prepares this opaque field in which it can put whatever it wants to put in. It could put in a message authentication code or even leave that out if it wants to, if it doesn't care about that part. So it's completely up to the autonomous domain to implement any function it wishes. So what we've implemented is a efficient message authentication code based on AES that only requires one AES rounds for verification. And so that is really super fast. Then again, it's only the 40 cycles, which takes as little as 10 nanoseconds on a high-end CPU. And so all the slow signature verification or signature generation is done in the control plane that has no effect on the actual data plane forwarding. So hope that, or? Mm-hmm.
Yeah, that does answer the question, thank you. And just kind of a follow-up question, when you have situations like route flapping, mm-hmm. Does that create significant overhead when you have to do the calculation?
So essentially, so that's a good question. So in route flapping would mean that paths keep changing, but in Scion, you always discover multiple paths anyway. So every 15 seconds, Scion would send out, currently we implemented 5 different paths that are being sent from over every link. So every autonomous domain sees all of their neighbors. They see all the links going to each neighbor. And over each link, they send 5 different paths every 15 seconds. So there's no inherent notion of route flapping in this case, because every 15 seconds, one receives just 5 other paths how to reach the ISD core over that link. And essentially, the data plane is completely insulated, and the destinations do whatever they want to do with their paths. They could keep updating their own paths. They could keep uploading new paths to the path server in the ISD core, but they don't have to, right? And the nice property is that it's a unicast operation, right? So today in BGP, when you have route flapping, BGP updates are flooded, right? So when a path changes, it can create a lot of different path changes downstream. But in Scion, if an end domain keeps updating its paths, it affects, and it's only being sent via a unicast message to the core. So nobody would really be affected by that. Right. So it's very efficient at the network level. Right. Right. Other questions? All right. So thanks so much for coming, and enjoy the rest of the week. Thanks. Thank you.